Now let's talk a little about the product. Bituminous polymer membranes are heterogeneous products composed of three principal components: bitumen, resin and filler. Bitumen is a distillate derived from the distillation of petroleum cracking. Resins are components that allow the membrane to maintain its properties over time. In other words, if we were to make a bituminous membrane without resins, it would have a very short lifespan and lose its main chemical characteristics rapidly. Resins can be grouped in two main families: APP resins and SBS resins. These are acronyms. APP stands for atactic polypropylene and SBS stands for styrene butadiene styrene. The difference between the two can be quickly explained. SBS resin, an elastomeric resin, makes the membrane particularly flexible and malleable. It's a synthetic thermoplastic rubber which, when mixed into the bituminous polymer membrane's compound, provides qualities that are very useful in cold climates or whenever an extreme elastic membrane is required. The second family of modifying resins is known as APP, or atactic polypropylene, a byproduct of the process used for the production of polypropylene, a component of many products that we use every day. This resin gives the membrane better mechanical strength and flexibility. Resins are fundamental, but not so much the quantity as the quality and the constancy of their characteristics. Because, as I said before, a bituminous membrane without resins would have a very short lifespan. It's also true that in order to maintain constancy in production, the selection of the raw materials inside a laboratory like this one is a fundamental step in maintaining the quality of the product. These modifying resins are responsible for the duration and chemical physical performance of the membrane. But it's also important to understand how the resins work and how they are amalgamated into the bituminous mixture. These photos illustrate the dispersion of the resin inside the bituminous mixture. As you can see, the homogenization of the resin is all the better and more constant to the degree that the quality of the resin is better and constant. Here's an example of excellent dispersion. The green part is the resin. The black part is the bituminous mix. Here instead, we can see how a lower quality resin provides unsatisfactory dispersion. It's a little as if we were incorrectly lubricating the engine in our car. The oil might be there, but it fails to arrive constantly and evenly to all vital areas necessary, as occurs in this second photo here. A bituminous polymer membrane invariably contains a reinforcement structure, both in order to permit industrial production and to ensure the product greater mechanical strength. These reinforcement structures can be divided into two groups, even if only one is present in 90% of the products on the world market. The first is vitreous coating. 20 years ago, reinforcement structures were made exclusively with vitreous coating, and this is an inorganic substance with a very low mechanical strength and an evidently nil elasticity, and therefore very low stretching and tearing resistance. In the last 20 years, the production of non-woven polyester has developed enormously, at least from the industrial point of view. Firstly, because it's not a fabric, or in other words, it's a non-woven fabric with a weave of filaments of fiber that does not have a regular warp. This is what the famous term non-woven fabric really means. Latest generation reinforcement structures are even reinforced inside by filaments of fiberglass. This is because even if polyester has remarkable properties of mechanical strength, it cannot ensure the dimensional stability offered by vitreous coating, precisely because vitreous coating is an inorganic substance. Today's technology allows us to combine the excellent qualities of dimensional stability offered by vitreous coating with the excellent mechanical strength of polyester. Fabrics are an essential component today because not only do they offer better workability and resistance, but they also guarantee the stability of the layer of final product at the worksite under any conditions, such as thermal shock, the dimensional instability of the support surfaces, etc. Mechanical strength is tested using this machine, a dynamometer, a precision instrument that measures a product's mechanical resistance to traction in both the longitudinal and transversal directions. This test is regulated by strict norms and must be scrupulously conducted. These spindles are 5 centimeters. And for this reason, the mechanical strength value that you see indicated on the technical data sheet is expressed in newtons per 50 millimeters or 5 centimeters. This test must absolutely be conducted in a laboratory, and in certain cases, even at specified temperatures, because high or low temperatures can alter a product's mechanical strength. All this goes to show that mechanical strength tests conducted at the worksite do not have the same reliability as those conducted in the laboratory. Now, with the help of my colleague, I'll explain the significance of the cold flexibility test, and perhaps one of the most important and widely known tests in the world of bituminous waterproofing. This test is conducted exclusively in the laboratory and consists in dipping a sample of material in the dimensions prescribed in a glycol solution that will progressively make the sample colder and colder at 5-degree intervals, such as 0 degrees, -5 degrees, -10 degrees, etc. After this conditioning, the requisite 2 hours serve to guarantee that every molecule in the product has the same temperature. The sample is folded in half by 180 degrees for 30 seconds and placed beneath a spindle of 30 mm diameter. If this spindle does not puncture the upper part of the membrane passes the cold flexibility test. This test is very important because it indicates the quality, the quantity and the capacity of the product to be bent at low temperatures. One thing must be made perfectly clear, however. The cold flexibility test does not have anything to do with the ambient temperature. In other words, if our product has a -20-degree flexibility, this doesn't necessarily mean that we can use it at a temperature of -20 degrees. The material would break anyway. This is just a laboratory test that indicates a product's chemical properties. Therefore, no confusion must be made between cold flexibility and the minimum conditions for use at the worksite, which in any case should never be prohibitive. A membrane should never be laid at temperatures of less than 5 degrees or at the very lowest 0 degrees centigrade. Now we'll talk about the penetration test. The penetration test, which our colleague will help us see, is an important part in the product evaluation process and is conducted on both the raw material, the bitumen, and the compound, or in other words, the bitumen already enriched with resins. The test consists in pushing this needle into the bituminous mass. The softer our bitumen compound is, the greater the penetration will be. Test results are expressed in tenths of millimeter, and this important parameter helps us understand how workable the compound will be on site, how malleable it will be, and how easy it will be to melt. Here we are at the productive unit's real brain or nerve center, the process control room, the technological heart of bituminous polymer membrane production. These computers allow us to control not only exactly what's going on in the production lines, but even the composition of the individual mixes that will be used to produce the materials to be distributed in the market. Each of these terminals is dedicated to a precise working phase, the tapping of raw materials, the type of product being produced, and the characteristics of that product. This represents the state of the art in reducing to a minimum the differences in quality level between one product and the next. Constant equality in the materials is one of the objectives to which the company has dedicated greatest attention and is one of our proudest accomplishments.